Hi everyone, let's work through the inference lab today. The idea of this lab is to start to get you thinking of using normal distributions to help us model and understand a variety of kinds of decisions we make with data. And the first question, I think, gets everybody hung up a little bit, primarily because we've either switched our brains to think with these abstract normal distributions, or we think about things like graphs and data, and it's hard to sometimes put these abstract models together with the data that we see. And so the first question really is supposed to help us see that normal distributions are kind of a model, an approximation, an abstraction of a fairly typical histogram. And the histogram is really just a kind of fancy bar chart. So really, normal distributions are like fancy bar charts. All right, so let's take a look at this fancy bar chart in particular. Here it says that suppose we've collected data on the weekly number of failures of a certain mechanical component. You've created a histogram using the counts of the number of times you have seen that many failures during the past 400 weeks. So using the histogram, what is the probability of exactly 12 failures in a week? So that's just asking us to look at this one little bar here of 12. And that looks like it's about 35, let's say 36. We know that n is 400, right? Down here, this is the number of failures. In a week. And over here, this is right, the number of weeks with each number of failures on our y-axis. So here we go, 12 failures in about 36 weeks. And so that's 36 out of 400. And that's going to give us about close to 9%, right? 0.0875. Using the histogram, what is the probability of 12 or more failures in a week? So instead of 12 failures, we're now asking for 12 or more failures. So that would be 36 plus, looks like about 30 plus 18 plus 5 plus 1 plus 2 plus 1. And that's going to equal 93-ish. We got something close to that. That's fine. We're going to take that 93 out of 400, and that's going to be equal to about 23% chance, right? So about 23% of the observations of these failures are going to have 12 or more. So if we wanted to think about what's the using present data to predict something about the future, we would say that we would expect, right, that about 23% of the time we get 12 or more failures. So I promised you we were going to think of normal distributions as kind of approximations of our histograms, and that's what we're going to do in part C. So instead of using the histogram, we suppose we're going to think of this as an approximately normal distribution. No more counting required. So given that the mean is 10, and the standard deviation is 2.4, use that information to calculate the probability that the number of failures is greater than or equal to 12. So if I was approximating, I would say that that's about 1 standard deviation. So up to the mean, right, we have about 50%. then from the mean to one standard deviation, right, we have about another 34%. So we could say that roughly, right, 84% of observations lie below 12. So about 16% of observations, let's make that blue, lie above 12. So, right, approximately 16%, right, 0.16. If we want to be more precise, we can go to R or Excel or use one of those tables at the back of a statistics book. And what you're going to ask R to do is use the P normal function and tell it that you're going to want P normal of 12, 10, and 2.4. And tell it lower tail equals false. If you want to do this in Excel, you're going to tell it to do normal dot distribution and 12, 10, 2.4, and it's going to give you actually because there is no lower tail false there, I'm going to tell it 1 minus normal distribution in Excel. So here's your R version, here's your Excel version, and the answer it's going to give you is going to be about 0.2. I can go ahead and show you what that code looks in R, like in R. Here we go, here's some code. I'm going to set my, let me put those up. There, we're going to set our X as 12, right? Our standard deviation, 2.4, and our average is 10. And we're going to go ahead and run that P normal to calculate it, like so. Gives you 0.202. If you want to have a little fun, I went ahead and graphed it here in ggplot. You have instructions to do something fairly similar. Oh, I should probably have loaded ggplot first. And you get a graph of what that looks like, what area we're talking about, that 20% under your normal distribution. Fun, right? All right. Back to our inference lab here. The normal distribution and its properties. 95% of students that we have are between 1.55 and 1.95 meters tall. Assuming the data are normally distributed, we want to know what is the mean, what is the standard deviation, and we're going to use the graph to go ahead and tell this story. So, here we go. So what's the mean? Well, the mean is going to be, if it's normally distributed, halfway between 1.55 and 1.95 meters tall. I think the easiest way to say is that 95% of students are between 1.55 and 1.95 meters tall, which sounds like plus or minus 2 standard deviations of a normal distribution, right? That 95% is usually plus or minus 2. So we can go over here and label 1.55 and 1.95. We could take the average of those two, add 1.55 plus 1.95. In the middle, I think you will find 1.75. That means that in between those two, right, is 1.85. And over here is 1.65, which means our standard deviation should be 0.1. We're adding 0.1 at a time. And the mean is 1.75. Suppose a new classmate is 2.05 meters tall. How many standard deviations is he above the mean? What is the probability that a randomly selected classmate will be 2.05 meters tall? Well, 2.05 is another, if we had labeled our graph nicely, we would have added our third 2.05. We can also go over here and go 1.45. So 2.05 is 3 standard deviations above the mean. And if we know something about normal distributions, that means that there's about a 0.1% chance, right? So the probability is equal to 0.001, or about a 0.1% chance. Okay. When comparing averages between groups or sections of data, we can apply the central limit theorem to test if differences are large enough to make us believe that there is a true difference between groups. So what does that mean? So the first question is asking you essentially, right, the core point about the central limit theorem is that sample averages, regardless of the underlying distribution of your data, tend to be normally distributed. Given information about the sample, such as its mean, its standard deviation, and its sample size, n, what is the mean of the distribution of the averages? We tend to assume we don't know anything else, so we assume that it's going to be the mean of the sample. Right? In the absence of better information, that's all we can do. The standard deviation, right, of the averages, we're going to take the standard deviation S and divide it by the square root of n. So if we're going to go ahead and do some calculations here, if the sample standard deviation is 15, the standard deviation for different sample sizes, we're going to see this is going to be 15 divided by the square root of 25, 15 divided by the square root of 30, 15 divided by the square root of 50, and 15 divided by the square root of 75. That's going to be for us 3, 2.7, 2.1, and 1.7. This should all help you kind of see, right, that as the sample size gets larger, our standard errors are going to get smaller. That the variation in the sample means that we get is going to be driven by the amount of underlying variation, that standard deviation, the numerator here, and right? The denominator, as the denominator grows, as we get bigger sample sizes, we should get smaller sample standard errors. All right, so again, we're going to employ our central limit theorem here. You have a history of 100 observations of equipment repairs. The mean time is 50 minutes, and the standard deviation is 20 minutes. So the mean of means, we're going to assume is 50, so we'll still put our 50 down there, but we need to calculate our standard error. That's going to be 20 divided by the square root of n, which is 100, which is going to be equal to 2. I'm lazy. I like easy math here. All right, so our normal distribution for the mean is not the normal distribution for the sample, right? For the sample, if we assumed it was normal, it would be our standard deviation of 20. So one standard deviation would be 70, then 90, then 110. But for the means, right, we expect them to be much more tightly clustered. Right? So while we can see lots of variation in observations, we wouldn't expect to see anywhere near so much observation in means, right? We would expect that the average, there's this pull of things towards the average. So while you might get an absurdly tall or an absurdly short classmate, you wouldn't expect a class that was tall on average, absurdly tall on average, or absurdly short on average. While you could have a day where the repair just took 72 minutes, 150 minutes, right, 220 minutes, would you expect to have an average of 220 minutes from the same sort of process that used to give you a mean of 50 minutes? No, nowhere close, right? Practically impossible to get, to be so unlucky as to get that kind of crazy average. Hence, we expect means to be fairly close together. And the more observations we gather, the closer we expect that mean to be to the true mean. So here's what we can do. So we're going to go ahead and label this in terms of our means. We have 50, so 52, 54, 56, 48, 46, and 44. Having a little fun with color. If a new system leads to a new mean of 48 minutes, how confident are you it represents an improvement? Well, that's at -1 standard errors. It asked us for a 95% confidence interval first, which I should have given you. Let's go ahead and do that first. Our 95% confidence interval is going to be plus or minus, in this case, 2 standard errors, approximately. Technically, it's 1.96 standard errors, but if you go ahead and do that, right, you have roughly your 95% confidence interval. So the technical answer to that, right, so this would be 46 to 54, sort of using a fairly normal rule of thumb. If you use the R formula Q normal, and you enter in, right, you would want 2.5% to be left over here, and 2.5% over here. So on Q normal, we tell it 0.025, 50, and 2. And then for the upper bound, we could do Q normal, and it's going to be 0.975, 50, and 2. And that's going to give you 10.8. I wrote down the wrong numbers here. One moment.